Okay, good morning, everyone. Uh, you're all very welcome to today's webinar looking at natural hydrogen exploration and the market opportunity. My name's Tiernan. I'm a conference producer here at Foresight Events, leading on the Foresight Webinar series. This event is sponsored by the Foresight event, which you can see on the background behind me. It's our all-energy clean tech show looking at the UK energy transition taking place next February in this lovely building. I don't know which side there we are that you can see behind me. That's the Titanic Hotel in Liverpool. So if that is of interest, please do give me a shout and be happy to discuss further. But for today, we're looking at natural hydrogen and the market opportunity, as I said, and next steps for exploration as well, and what's needed. We're all very familiar with the hydrogen market now. I think it's been talked about and explored for a while now as a source of clean energy. But most of the conversation, as we all know, has been around manufactured hydrogen, specifically green and blue hydrogen through electrolysis and fossil fuel reforming. Natural hydrogen is, of course, different. It's formed underground through natural geological or even biological processes without the need for heavy industrial input as well. And recent research suggests that there may be vast quantities of it. But this relies on some very important parameters, of course, around depth, accessibility, and also purity of the hydrogen there as well. So the potential benefits there are compelling. It could be very low cost, low carbon, and low footprint as well. And there has also been successful implementation of natural hydrogen as a fuel source in Mali, albeit very low scale. So the benefits are there, but I think that the conversation is how we get there, um, and how we capitalize on that as well. So it's still very early stage, lots to map out and discuss. Hopefully, we'll discuss a lot of that today. We've got three great speakers. I'll introduce them now, all in one, and then they'll, of course, elaborate on who they are a little bit more. So we're going to start off with Richard Heath, who is a consultant and commercial director for the Natural Hydrogen Study Group. And Richard, you're based here in the UK. Then we're going to hear from Dr. Arnout Everts, who is an energy consultant at AEGO. Arnout, amongst other roles, is also a member of the Hydrogen Science Coalition as well, and has 35 plus years of energy industry experience, mostly in the oil and gas industry. So lots of knowledge there to tap into. Finally, we're going to hear from Max Brouwers, who's Chief Business Development Officer at GTEC. Max leads the growth for all of GTEC's priority sectors, including hydrogen, CCS, geothermal, and also strategic minerals as well. And Max, I think you started your career at Shell as well, where you previously VP for exploration for Europe, Russia, and the Caspian as well. So breadth of knowledge here, all very intimately involved in the natural hydrogen market. Really looking forward to hearing what you have to say, and then getting into a good Q&A session afterwards as well. Please do, as always, as I always say, please feel free to pop your questions in as and when they come to you. We're going to bank them all, and I'll be able to ask them all to our panel once they've all spoken at about past. So without further ado, lots to get into. So we'll get started. Richard, I'm going to hand the floor over to you. I think you've got some slides which I'm sharing. Let me do that now.
Lovely, thanks, Tiernan.
No, you're very welcome. They should come up in just a moment. And yeah, Richard, just tell me when you want them to move on and I'll be able to do that. There we are. You should be able to see them
Lovely.
now.
That's great. Thank you, Tiernan, and thanks for this opportunity. And good morning, everyone. Yeah, my name is Richard Heath. I'm a geologist. I graduated from the Royal School of Mines in the mid-80s and did a master's in mining geology at Camborne School of Mines in the southwest of England. Started my career working for NIREX, which is a government agency responsible for the disposal of geological nuclear waste deep geological disposal, which gave me some insight into fractured basements and so on, which is quite useful in the current studies that we're working on. I worked then primarily in the oil and gas industry for the last 25 years and in hydrogen for the last 4 years or 5 years. So Tiernan, if we have the next slide, please. So the Natural Hydrogen Study Group, it does what it says on the tin, really. We formed in late 2021. We've been studying natural hydrogen systems in the last 4 years. We've looked at a variety of geological settings, including passive margins, intercratonic settings, such as Marley, convergent margins, and a lot of work in ophiolites. We're a team of about 10 people. We all know each other. We've all worked together for many years, and we're a multidisciplinary team. So most of us are petroleum exploration in background, but a number of us have minerals exploration backgrounds, and as you can see, we have experts in different roles, which is very important for trying to understand the natural hydrogen systems. We've spent 4 years really trying to work out if it's a real thing. We've been looking at some of the myths, but we do believe there is potential for hydrogen to be generated in the subsurface and to accumulate in reservoirs that we can potentially exploit. So using our expertise from the minerals and oil and gas sectors, and using a science-led exploration approach, we think it is possible to locate natural hydrogen occurrences, and we have developed predictive models in a number of different settings to try and help that exploration process. Our focus is that serpentinization is the key geological process that will generate potentially significant volumes of hydrogen. The cartoon here just very simply summarizes some of the differences between the hydrogen system and a petroleum system, which many people will be familiar with. The hydrogen system is a more complicated beast, in that the source rock for the hydrogen is probably within the basement, whereas in the petroleum system, your source rock is generally part of the basin itself. In the hydrogen system, you need the interaction of water, or certainly for the serpentinization process, water is required to interact with the rock at a certain temperature and therefore a certain depth in order for the hydrogen to be generated. In both cases, hydrogen or methane gas can then migrate through the subsurface and can accumulate in reservoirs with traps that can seal, and then you can exploit those reservoirs in theory. There are losses for hydrogen, but we do believe that you can trap hydrogen effectively. So next slide, please, Tiernan. Okay, so in this slide, I've adapted a figure from a publication by Klein et al. In 2020, which summarizes 4 of the main subsurface processes by which hydrogen can be generated within the Earth. I've rejigged the figure and just put the 4 processes in order of scale. So hydrothermal alteration, radiolysis, volcanic degassing, and mechanoradicals. And Klein et al. Have come up with estimates of the amount of hydrogen per year that is generated by these different processes. And as you can see in the graph on the bottom left, the annual generation of hydrogen is dominated by hydrothermal alteration, which would include the serpentinization process. And radiolysis is in second place. This is global annual generation in the subsurface. Volcanic degassing can be significant, but most people pay attention to hydrothermal alteration and radiolysis as their preferred sources. We like serpentinization because the source itself can be considered to be a point source. The geometry of the rock is probably better defined, whereas radiolysis can be generated in different geological environments, but over a much wider area. So you have a more dispersed source than your point source from serpentinization. The process of serpentinization, the generation is very, very rapid in comparison to radiolysis. So we're looking at generation in the terms of thousands of years from serpentinization, whereas radiolysis, you can accumulate hydrogen over millions of years. And another consideration is this phase in which the hydrogen is generated. And we believe that through serpentinization, hydrogen can be generated both in the gas phase and as hydrogen in the solution in the aqueous phase. The next slide, please, Tiernan. So in the work that we've done, we've adopted a certain sort of set of guiding principles that govern how we address our different studies. We believe that hydrogen behaves much like hydrocarbon gases in that it is generated in the subsurface, it migrates through the subsurface, it can be sealed and trapped in different geological environments. And then we can adopt then, when we look at exploring for hydrogen, a systems and play approach that would be adapted to the specific geological environment that we're looking at. Couple of publications mentioned on this slide: Hutchinson et al. 2024 and Jackson et al. 2024. These are open source publications or open access publications that we've been involved in the preparation of. And these references really define what we're about. We think it's very important to be looking for gas phase hydrogen rather than hydrogen that might be in an aqueous phase for commercial considerations. And I think Arnaut will discuss that later in his presentation. But we believe that the hydrogen in the gas phase, it can be concentrated in both space and time from ideally a point source. Now, a rock can generate hydrogen from serpentinization at different times in its lifetime, if you like. So you have to both consider when is the hydrogen being generated, how does it migrate, and how can it be captured. And as I've said, we believe that serpentinization we think it's the only commercial source of natural hydrogen at scale. And again, the scale of what we're looking for, Arnaut will discuss. But always, we're looking for gas phase hydrogen. And when it comes to which rocks can produce hydrogen, we believe that ultramafic rocks are the most prolific producers of hydrogen. And so we're considering, for example, mantle rocks and layered intrusive rocks as as the preferred source rocks for hydrogen. In terms of where serpentinization occurs, well, we know that there's active serpentinization of mantle rocks in different geological settings, including mid-ocean ridges, passive margins, within ophiolite bodies, and in subduction zones as examples. But also, hydrogen can be generated in onshore settings. And there are a number of onshore settings where mantle rocks exist. We might be thinking about ophiolites and greenstones in this case. And we can develop exploration play models for these different geological settings. So if we could have a look at the next slide, please, Tiernan. Okay, some cartoons. These are out of the Jackson et al. Paper. On the left-hand side, you have offshore settings primarily offshore settings, and on the right-hand side, we have onshore settings. Just to get your eyes into the colours here, mantle rocks are shown in sort of a pinky colour. Continental crust is in the yellowy colour, and sedimentary sequences are shown in the brown. We have done studies in all of these different areas. So, for example, the rift exhumed mantle setting, we might think of Mali. Is one setting. The rift inversion orogenic setting on the top right. We might be thinking about the Pyrenees in this case. Mali is in the greenstone case on the bottom right, and accretionally orogenic setting, maybe the Somale-ophiolite, for example, in Oman could be an example there. So hydrogen can be generated in, we know it occurs in the offshore settings to the left, but onshore work is the current focus for exploration because it's cheaper to explore onshore than it is offshore, and cheaper to develop anything. So if we can move to the next slide, please. So one of the areas of research that has provided some interest is how you evaluate hydrogen yield from a given source rock. There have been a lot of published papers on laboratory studies, and there is open source software that you can use to try and model hydrogen generation. So we have an approach. We've called it HiEval, and using HiEval, we look to evaluate and quantify hydrogen yield from a volume of rock, and this gives us an idea of source rock potential for the serpentinization process. So in the graph, you have temperature from 0 to 400 degrees C, and potential hydrogen yield expressed in tons per cubic kilometer of rock. Okay. The dashed line in the graph, this is what we use as a control point. This is fosterite, which is an olivine mineral, and that you can see tracks up and generates hydrogen at higher temperatures. So we're looking at up to sort of 330 degrees C in that graph, at which point it tails off very rapidly. So fosterite is our, if you like, control point. Now, the other lines on this graph are from different rock types.
Richard, sorry to interrupt. Just going to give you a minute warning there, if that's all right. Just conscious of time.
Oh, okay. Anyway, so these source rocks are great producers of hydrogen, but not all source rocks are equal. So the important point about the HiEval process is that it allows us to compare different rock types and rank them, and also we can use the process to assess the phase in which hydrogen is generated. Right, I've got 3 slides. The Royal Society briefing came out in May this year, and this has concluded that the UK does have potential for natural hydrogen. It again focuses on radiolysis and serpentinization as processes by which hydrogen can be generated. There are no databases for natural hydrogen occurrences, and there has been within the UK no coordinated nationwide exploration to date. It highlights the importance of having predictive maps to try and generate target areas. Next slide. BGS has just published a report on the UK potential. It is a very high level screening program. They've identified different geological terrains within the UK, and they've effectively graded them as those areas with potential for natural hydrogen and limited potential. So on the left-hand side, the potential grade areas are shown in the blue, and the limited potential grade are not shown in any colour. And it might be surprising that some of the southwest does not have potential grade. But that's just a passing comment. And then next slide, please, just to wrap it up. So this graphic is from the Royal Society report. It shows how a commercially viable natural hydrogen industry could take place within the UK. Our expertise at NHSG is in the blue, how you generate hydrogen and accumulate it. But it's very much, yes, the industry is in its early stages, both in the UK and globally. We're still at early phase of exploration. Benefits of natural hydrogen are expressed here. I would say that it potentially is cheaper than green hydrogen. And that in order to encourage exploration, we need regulations and permissions. So we need legislation that allows companies to explore for hydrogen. And other countries have adapted their legislation, and I think we are yet to do so in the UK. And that is it. Thank you.
Richard, thank you very much indeed. Really, really good start and overview there. I'd be interested to hear a bit more about some of those things in the Q&A session, specifically around the new kind of policy type developments we've got in this country, and also that high eval as well. Very interesting stuff. Arnout, I'm going to head straight over to you now if you want to start sharing your slides.
Yeah.
Got about 10 minutes or so. Please go ahead.
Okay. Okay, put it in slide view. See if I can hide this thing. Can you all see my slides?
Yep.
Excellent. Just a little bit about myself. So I'm Arnout Everts, also a geologist by background, and I've worked for over 35 years, mostly in oil and gas. Initially with Shell, and then with Petronas in Malaysia, and then in consultancy. And in my consultancy work, I've done a lot of what's called techno-commercial due diligence and project viability work. And also I've done a fair bit of what people call resources and reserves assessments and certification. So a lot of my more recent work focuses on what it takes for projects to basically evolve into value, what it takes for resources, potential and prospective resources, like what we're talking about with natural hydrogen, what it takes for these resources to eventually be exploited and produced at industrial scale, and therefore result in value for the investors and for society. So the way I look at natural hydrogen is also very much from that perspective. So the slides I'm going to share now they're kind of leading on to what Richard just now explained, but it's really taking a slightly different angle, namely looking first, okay, where is hydrogen currently being used for? What are some of the other proposed usages of hydrogen in future energy systems? And how much hydrogen would we need to basically supply industrial applications? And then what would it take if we wanted to have some of this hydrogen come from subsurface hydrogen, so natural hydrogen? So let's start with, okay, how much hydrogen do we need to decarbonize industries? Because at the end of the day, the reason why people are talking about hydrogen and hydrogen economy is because we realize we need to reduce emissions and do it fast in order to avoid excessive global warming. So we want to decarbonize industries. Now, how much hydrogen is currently being used in the industry, and what is it being used for? So if we look at current usage of hydrogen, which is around 100 million tons per year, most of that hydrogen goes to two applications. One is ammonia plants, so that's fertilizer. Ammonia is NH3, so it's basically nitrogen and hydrogen, and this hydrogen needs to come from somewhere. So therefore, ammonia plants, and ammonia is basically one of the key sources of fertilizers. These use hydrogen, and they use big quantities of it. Here, this bar graph, note that the vertical axis is logarithmic, so it starts at 10 and it tops at 1 million tons per year. So you see a typical ammonia plant needs close to 300,000 tons of hydrogen per year, so enormous quantities of hydrogen. Then a second big usage of hydrogen right now are petroleum refineries. So, and this is because to crack long chain organic molecules into shorter chain organic molecules, you need hydrogen to kind of, when you cut the molecules, you need to top it up with hydrogen. So a typical petroleum refinery needs about 50,000 tons of hydrogen per year. And even if we look into the future, since we still need petroleum products for chemicals and plastics and all this, some of this hydrogen demand from petroleum refineries is going to stay. And then a third big industrial application that people are talking about when it comes to hydrogen is decarbonizing steel plants. And a typical steel plant would need about 70,000 tons of hydrogen per year. Just to give an example, the green steel plant that had a lot of recent media focus in Germany, a project by ThyssenKrupp in Duisburg, it needs about 110,000 tons of hydrogen per year, and the cost to convert this plant from running on coal-fired furnaces right now to hydrogen-fired furnaces would be around 3.5 billion euros. So these are massive amounts of money as well that it takes to basically convert steel plants to hydrogen. But anyway, so industrial applications, big amounts of hydrogen. And then people are talking about potentially using hydrogen for other things at smaller scales. Like here, there's a few examples listed: district heating, hydrogen vehicle fueling hubs. If basically in the future a lot of the road transport would be using hydrogen, and then maybe even more speculative hydrogen jets maybe in the future. And so you see that still for example, a commercial hydrogen vehicle fueling station, you need about 1,500 tons of hydrogen per year. So even the smallest type of industrial application would still need at least over 1,000 tons of hydrogen per year. So fairly sizable quantities. And then not only the amount of hydrogen that you can supply from, for example, a natural hydrogen project matters, also for how long you can sustain the supply, because investment in hydrogen infrastructure, for example, building a hydrogen fueling station, let alone converting a steel plant to run on hydrogen, this costs massive amounts of money. I just now mentioned the example of the steel plant in Germany, 3.5 billion euros. So Mr. ThyssenKrupp, when he wants to sign a gas sales contract with the supplier of hydrogen, he wants to make damn sure that this supplier can supply hydrogen at the required quantity and purity, not just for a week or a month, but for many, many years. So ability to sustain these production levels for a long time is going to be key to commercialize hydrogen. And then when we then compare these amounts of hydrogen that may be needed to decarbonize industries, if we compare that with how much we've been able to flow from natural hydrogen test wells, we start seeing the problem. So here, the same graph, just the large industries and the smaller hypothetical offtake opportunities are on the left. And then on the right are the rates achieved to date from natural hydrogen test wells. And note that I've expanded the scale now of the vertical axis further downwards, because otherwise you can't even see the natural hydrogen flow tested wells. So there's basically here the biggest is this purple bar. This is the Bougou field in Mali, where the only producing well drilled to date has flown 1,500 cubic meters of hydrogen in a one-day test. That equates to about 50 tons of hydrogen per year. And other tests, for example, in South Australia, gold hydrogen, Ramsay is around 7 tons of hydrogen per year. And then in Kansas, on the US Midwest Reach or Reef system, their rates are even less than a ton of hydrogen per year. I mean, if you work out these few days tests to what it would be in a year. So we're at least 2 to 4 orders of magnitude below what's required for even the smallest industrial application. So really we need to scale up these rates big time. And whether we can do this remains to be seen, because for prospects, I've shown here a few examples on the right, people assume much bigger, much higher rates that could potentially feed big industries. So in the rate a few thousand tons of hydrogen from one well per year. So then for example, if you get 5,000 tons of hydrogen per year and you want to feed the petroleum refinery, you need 10 wells. Whereas if all I can get is Bugu, 50 tons of hydrogen per year, then for a petroleum refinery I need 1,000 wells, and you just right away see it doesn't work. But these prospective rates are in settings where we haven't found any hydrogen yet, and we let alone have we tested this. So this is purely speculative. And then how these, even if we could achieve these rates, whether we can sustain them over longer periods of time is also a big question mark in the kind of settings where people are now looking for hydrogen exploration. The rocks are typically very tight and fractured, and in tight fractured rock, gas well rates typically decline over time, and sometimes they decline very fast. And this has to do with the fact that assessing resources far away from the well is much more difficult in a fractured reservoir than just around the well. So there's a risk that these rates, even if initially they're good, they could decline very fast. And all of this would have to be appraised basically as part of exploring a hydrogen prospect. Then
Arnout, just giving a minute warning there for you.
Oh shit! I'm already almost done. Damn. So then let me rush up then a bit. So about resources and reserves. So in the industry, people are talking about 3 main categories: prospective resources, which are basically resources that may or may not be there, and yeah, we haven't proven any of it, let alone recovered anything to surface. Then contingent resources, which are, okay, now I've discovered presence of a resource and I may have recovered some of it to surface. But I don't know whether or not a project could be commercial. It's pending resolving either technical issues, so for example, proving commercial rates, or firming up regulatory requirements, or also doing technical studies on the facilities, whatever. And then reserves are resources that are either on production or firmly committed to production with all the approvals in place, the resource base proven up, and also funding committed. So, and to go from the one to the other, there's lots of stuff you need to do. Now, most natural hydrogen ventures are at the bottom of this category, at the player concept stage. Much of the exploration to date is limited to redrilling of old wells with high gas shows. That's what in the US, companies like Hytera, in Australia, Gold Hydrogen, what they're doing. They're not really testing carefully high-graded prospects. They're just redrilling old wells where there were some hints of hydrogen. So that shows that there's not a lot of confidence yet in these exploration models, and we're very, very early on. It will take a long time to mature exploration ventures to portfolios of drillable prospects, and then hopefully make discoveries, and then carefully and methodically mature those and then that means that even in the most rosy scenario, walking this whole way from basically from concepts and hypothetical place where we are now to commercial ventures, this is not going to happen overnight. And I just want this is the last slide I'll show. When we compare hydrogen versus methane, So methane is the main component of natural gas. Then one of the things we see is that the so-called volumetric energy density, how much energy is in an amount of high volume of gas. If this gas is hydrogen, the amount of energy stored in it is only a third of that of methane. And as a consequence of that, if we want to basically find a hydrogen field that has the same amount of energy stored in it as a natural gas field, we need to find a hydrogen field that is 3.5 times as big as the natural gas field. So either the area needs to be 3.5 times as big, or the net pay needs to be 3.5. So instead of say 10 square kilometers, I need to find 35 square kilometers, or instead of 50 meters net pay, I need to find almost 200 meters net pay. So the challenge is there, finding these quantities of hydrogen. I think I'll leave it to that.
Arnout, thank you very much indeed. Lots to consider there, and lots to bring out in the Q&A session. I think the message there is how important it is to manage the feasibility versus hype aspect of this conversation, and realize what's achievable now and what needs to happen in order to scale this if indeed we can. Max, I will hand over to you now. You've got about 10 minutes or so. If we can keep it to 10 minutes, that'd be great, just to give enough time for the Q&A session. But for now, I'll hand over to you.
Yeah, thanks very much. And yeah, I think actually Richard and Arnout have done a great job on setting the scene, so I should be able to go through this fairly quickly, because Richard really explained very well what the geological requirements are, and Arnout very much highlighted what the technical challenges are in order to make it commercial. So what I would like to do in this short overview is share with you what GTEC is actually doing in order to find those accumulations which are commercially attractive. And we leverage for that 4 specific items which we as an exploration company bring to the table. We've been in existence for 4 decades, so 40 years of exploring for natural resources, originally for oil and gas. And we are applying all that capability now also to find natural hydrogen accumulations. The source rock for natural hydrogen, again, as Richard highlighted, benefit very much from understanding the gravity and magnetics in certain kind of settings. We have a very large, or more specifically, the largest database for that. We have got a global knowledge database, which allows us, like an atlas of Earth's history, to go back and understand how a certain area looked like in a certain amount of time, hundreds of millions of years ago, to see if the conditions were appropriate. We're actively applying now also machine learning in order to help identify where occurrences might be, which with the human eye we haven't thought of. That's actually skills and capabilities which you bring in from our critical minerals analysis. And we also have great geospatial capabilities, which allows us to overlay the above ground challenges, such as distance, for example, to offtake, but also regulations. So the basic principles are exactly as Richard outlined. At a very high level, it is very comparable to oil and gas. We're looking for a source rock. We need to understand how from that source the migration takes place, how the hydrogen moves to a potential trap, which requires a reservoir and it requires a seal on top of it. Each of them at the same time have quite some differences as well. Again, Richard neatly outlined that there are different types of source rocks. We don't yet fully understand all their amount of potential contributions, so we need to consider that. Hydrogen is a much lighter molecule, much more mobile, if you like, so it migrates in different kind of ways. Also, again, given hydrogen's ability to interact with its surroundings, we need to start thinking about that as a trap. How easily does it percolate through it, but also how do we avoid bacteria potentially eating it, and so on. Again, the story has been told at a high level. We applied this methodology to predict where occurrences might be. What we haven't talked about, and just want to pause for a minute or so, is also the ability to add to the predicting capability a detection capability, i.e. where do we potentially see on the surface hydrogen, which might help us to further hone in where to go, what areas are high graded. And that can be from hyperspectral satellite images, for small depressions, or it might be actually soil sampling, trying to see where it leaks out. There are questions around it, but complementing that with prediction capabilities is, again, only making our overall toolkit stronger. So we developed a comprehensive workflow. Again, this is really at a high level, starting off at the basin kind of scale, looking at all existing data, a desktop type of study to understand where the potential is the greatest. That might lead to a recommendation to acquire more information, more geophysical, geological data before making a more expensive decision whether or not to start drilling at a certain location. And again, depending on the well results, we can decide whether or not to follow up on that, yes or no. There's just one specific example which I would like to highlight of the type of work which we can do with our gravity and magnetics, which again is quite different than oil and gas, but I think is really important. Using magnetics to start with, we are able to look in the subsurface at the amplitude and direction of the magnetic amount of magnetics, if you like. And that helps us to understand where potential rocks might be present, which allow for this serpentinization to take place, which is effectively oxidation of iron-rich rocks. And actually, we are now further refining that so that we not only can model or, if you like, quantify where those rocks are in the subsurface, but even start to do volumetrics. How mature is that source rock and how much remaining potential does it have to actually produce at this moment in time? And again, integrating that with other types of geology allows us to further high grade those type of source rocks. Again, just as an example of the different type of source rocks which we're looking at. And again, I know we're really short of time, so I just keep it at one more slide. What really is important in order to make the natural hydrogen sector successful is to consider three different elements. One is technical. We talked quite a bit about that today, from the exploration, the subsurface, if you like. Arnout spoke quite a bit about the development and production concerns which we have. But we also really need to consider the commercial aspects. What is the timeline before an opportunity actually can start producing? How do we finance this? Because offtake might not be guaranteed from the start. So backing the financing is challenges. And then we need to start looking also at the social aspects of it. Are there actually regulations in place? And many countries don't know yet how to deal with natural hydrogen. How does permitting actually work? Which regulator do I need to go to? And again, per country, that differs quite a lot. And last but not least, we also really need to consider early on stakeholders, particularly local stakeholders, who might not necessarily like oil and gas, and they start seeing or hearing about something which looks the same. Yes, burning natural hydrogen might be safe, but again, what exactly is it? And if we as an industry or interested parties in this don't take the empty space in media and other places in order to inform what natural hydrogen is and what the benefits of it is, we have a chance that it actually might result in a different kind of situation which we don't like. So again, what we really need to look at is certainly the technical aspects, but also keep our eye on the commercial and the social. And looking at all those three together might allow us to find the places at this moment in time across the globe which are more favorable than others. And GTEC has, together with partner Sound Energy, actually identified Morocco as a particular place where we're actually not providing, in this case, a service, but are actually working together with Sound Energy to pursue exploration ourselves. I will leave it at that and hand it back to you, Tjerden. I hope we've got still sufficient time for Q&A.
Thank you very much, Max. Yes, we do indeed. I'd be interested to hear a little bit more about that project as well, if possible. But I'm just going to start off with, as we move into the Q&A session here, then a couple of slightly broader questions just to get the conversation flowing. I suppose the first question I'd ask is, we've seen these studies come out about, the potential abundance of natural hydrogen. If that is indeed the case, what does the panel see as the kind of the single biggest factor that will determine whether it becomes a major part of our energy mix or not? And just to follow up on that, just in terms of that regulatory piece then as well, what do the panel see? What regulatory changes or incentives would help exploration companies move forward, and what needs to happen in that space as well. I know that, for example, in Australia, I think they changed their permitting process to allow for hydrogen exploration, their oil and gas permitting process, which I think helped the industry to grow there. Any thoughts on that? So the single biggest factor that would determine whether it becomes a large part of our energy mix, and also that regulation piece as well. Does anyone want to kick us off there? Richard, go ahead. And then
as far as I know, in the UK, there is no legislation that would allow companies to apply for an exploration license for hydrogen per se. So if the existing legislation were amended to allow companies to have an exploration license or even a reconnaissance license, then that could encourage exploration work to be undertaken in the UK. I think in France, they've adapted the minerals legislation to allow it. In the US, of course, so that the landowner in some areas owns the rights. So that has allowed the US to take place. But certainly, without a framework for companies to recover any exploration money, then there will be very little work done in the UK.
Thanks, Richard. Arnout, come in there.
I see basically two things that need to happen in order to get more and also bigger energy companies interested and convinced that natural hydrogen could really be something they could pursue and that could become a major part of the future energy mix. One is, like I showed already, commercial flow rates, like the attempts to flow hydrogen to surface to date are really minuscule. Even like another example I didn't show in the graphs, but which is quite anecdotal, is this very nice study done by a French group of researchers, Laurent Truchet and others from Grenoble University, who discovered hydrogen being vented from a chromium mine in Albania. And now they estimated that from this whole series of mine shafts, the amount of hydrogen evacuated and diluted with other gases is about 200 tons per year. And this 200 tons in the context of these numbers that I showed earlier is still nothing. It's probably not even enough to run part of if you can purify it enough to run basically a hydrogen genset or a generator, it's probably not even enough to power part of the mining operations itself. So really we need much bigger production capacity proven up, and this needs to come from well tests. And then the second thing that I would bring that I think is really important is it's showing presence of hydrogen in material amounts as a free gas in the subsurface. So most of the finds to date, they are actually hydrogen dissolved in formation water and maybe very, very small amounts of gaseous hydrogen in little pockets. And this basically, to produce dissolved hydrogen in material quantities means producing even bigger quantities of water. And you need to do something with this water. And the amount of hydrogen that comes with the water will be small because hydrogen is not very soluble in water. So you need gaseous hydrogen trapped in the subsurface in significant amounts, like a natural gas field. And we've been speculating that these kind of accumulations exist, but we haven't demonstrated any so far. So I think those two things is flow testing wells at rates that start to go towards the realms of commerciality, and then proving on the basis of gas flow test and also downhole pressure data that significant columns of gaseous hydrogen trapped in the subsurface, that they exist. The moment we have those two, I think more companies will start to become interested, and I think the potential for commercialization becomes more clear.
Thanks, Arnout. Max, did you want to come in there quickly?
Yeah, I just want to maybe add to both of your questions. First of all, what can governments and regulators do? I think making sure that there is transparent and stable regulations. which also need to reflect the very nascent nature of this. So the risk-reward balance needs to be appropriate, i.e. this should be stimulated rather than high taxes on producing some kind of resource. And related to that, what also will help is if governments can provide the historic subsurface data more available. So are providing platforms in order to download well, seismic and so on data to have more geoscientists work on it. Secondly, building on Arnout's point, I absolutely agree with the points which he made. I am maybe a glass half full or an optimist here. I also do believe that a lot of effort is going into developing new technologies which may allow us to develop hydrogen from resources which are currently not deemed commercial. Similar as we've seen maybe with shale gas, it took several decades for this to actually develop, and that was because new technologies were developed and needed time to develop to be commercial. I don't know yet what those technologies would be for natural hydrogen, but I can envisage a scenario wherein also other the non-standard, non-gaseous phase hydrogen accumulations become commercial. But as highlighted, that will take some time.
Thanks, Max. I'd love to get into a couple of those points, but we'll hold that for now because we've got a few questions. First of all, Amy Brown asks, thank you all for the brilliant presentations and slides. I have a question from Max and Richard. If hydrogen is pipelined to a specific area for commercial use, does the method of pipeline transport affect its overall efficiency, particularly in terms of energy loss, purity, or economic viability? Amy's also interested in how the location of potential source areas within the UK might limit or influence this efficiency. And then I'm just going to couple that with another question just for time. Jared Knott asks, is the current oil and gas workforce capable and able to reskill and redevelop tech to suit natural hydrogen? Is this one of the major benefits of natural hydrogen? Let me know if you need me to repeat.
Okay, I can have a go. Well, the second question first. Yes, there's plenty of the skills within the UK workforce are there. You're just applying scientific methods in a slightly different way because you need hard rock geology experience to understand the hydrogen system because of the importance of basement. But the skills are there within the workforce. The tools are there because we can adapt existing software to this new problem. And there are companies developing, specific software tools to model migration of hydrogen in the subsurface. So that's easy enough. On the pipelines question, I'm going to duck that one. We are explorationists. We will find the hydrogen. When the hydrogen gets to surface, somebody else will work out how to monetize it. That's, but first you need to find it in significant quantities. And until we do that, other questions then would follow.
Maybe I can try and attempt the part about the pipelines.
Sure.
So hydrogen is a much smaller molecule than natural gas. And there's lots of research that has also in the context of hydrogen storage that has shown that it's much more diffusive. So it tends to leak to virtually any sort of material. So therefore, production losses in if you're producing and then transporting natural hydrogen are going to be bigger than for natural gas. And I think the risk in term if there's a leakage is also significant because hydrogen is colorless and doesn't have any odor. So detecting hydrogen leaks is going to be much more challenging than detecting natural gas leaks. And then the third thing, which is also a factor of significance, hydrogen is considerably less compressible than methane. So therefore, in terms of energy, you would need to compress it to the same to take the same amount of space per unit of energy as methane. Yeah, it's considerably more. So it's not to say that it's impossible, but there are challenges, and these challenges are significant. And then as far as the pipelines themselves, if you say small pipelines that transport gas at relatively low pressures and with low flow velocities, there you can easily transport natural hydrogen or just any hydrogen through these pipelines that were designed for gas. But big pipelines, there it's not so straightforward. The risk of creating metal fatigue, because hydrogen basically creates brittleness of the metal. This risk is real. So in reality, if we're starting to produce material amounts of hydrogen, and we want to transport these via existing pipeline networks, then there are some technical challenges ahead, which can be solved, but it's not as straightforward as it may seem at first glance.
Yeah, and maybe Tiernan, just as a addition, but turning maybe Arnout's answer upside down. Clearly, there is benefit in finding hydrogen close to where your actual production is. So that is a much stronger driver than maybe what we've seen where oil and gas, natural methane type of gas is being transported all over the world. And we see that challenge, for example, with green hydrogen projects in Chile or so, trying to export their green hydrogen to Japan or so, and that's very challenging. So find it close by, or find it in such huge quantities that people start building their facilities where it's actually being found.
Yeah, it's a tricky one, that, isn't it? Because, unlike industrially manufactured hydrogen, you're kind of at the mercy of the earth there in terms of where it forms. And so that's, tricky one. And that will be, as Richard said, a key consideration as and when it's found is getting it to where it needs to be as well, in the most effective manner. Interesting points. A few more questions I'd love to get through here. Darren Andrews says, thank you for the fascinating presentations. One of the key opportunities with natural hydrogen is the potential for it to continue generation, allowing perpetual extraction of resources. Has this been demonstrated? Is it realistic?
Optimistic. Because the generation of hydrogen can occur very quickly. And there have been, people have cited Brouwers as an example where the gas is continuously replenishing from depth. But I guess my money would be on the conventional, let's trap it and store it in the subsurface and not rely on it renewing as you deplete.
Arnout, quickly there.
Let me add to that, and I can actually, maybe I show a slide again to illustrate my answer, if I can.
Yeah.
Sure.
Can you see my screen?
Yes.
Yeah.
And let me hide this thing. So this basically here is a slide that I showed a few weeks back at the Geological Society conference in London on natural hydrogen. An excellent conference, really, really high, very, very interesting discussions and lots of great presentations. So here, what you see is the top graph, the graph on the top right is showing so-called resource density, how much hydrogen per unit area you have in different places. And the one in blue here, this is one for one particular plate type, but it doesn't really matter which one it is. If you look very carefully, you see on top of there is another, so there's two bars. One is in place hydrogen, and how much, the second one, the dark blue, is how much of that hydrogen can I recover. And there's two little bars on top, extra slices on top. This is how much recharge you are likely to get based on the high end of global recharge rates per unit area. So the amount of recharge that can happen are very small relative to the amounts you need to produce if you want to supply industrial quantities of hydrogen. So yes, there is a chance that natural hydrogen proves basically a renewable resource, but the rate at which this renewal would take place is very small. It's almost negligibly small compared to the rate at which you would have to extract hydrogen to meet industrial supply. So hopefully that basically helps. So that's why I know there's a lot of excitement about that, but in reality, when you look at numbers, how much recharge per unit area can you expect, even if there's a lot of prolific hydrogen generation deeper in the subsurface, versus how much hydrogen you would have to extract in order to feed, for example, a small ammonia plant, then you see it's not going to work. You're going to run out of hydrogen resource at that site at a much faster pace, or you're going to deplete it at a much faster pace than you can expect it to replenish.
Thanks, Arnout. Max, very quickly
Yeah.
there.
Very quickly, one thing which you haven't discussed at all, and again, it's additive to what Arnout says, is human stimulated natural hydrogen. So there is the potential to accelerate through catalysts the production of natural hydrogen in the subsurface. That is a much less mature technology. And again, I have no numbers, but I could imagine that that could help to top up, if you like, these kind of fields a little bit quicker. So again, longer term, but exciting potential.
And
Now
better
it's interesting. Oh, sorry, go on, Richard.
Yeah, no, the stimulated hydrogen research is very, very well funded through the US, but I still don't know how they're going to catch the hydrogen that they stimulate. So,
That's exactly the problem. Indeed, so the encouragement is there in the sense that small field, so not only just modeling work and lab experiments, but small field trials in Oman, for example, they are encouraging. So it looks like with novel, less evasive stimulation techniques like electrical stimulation rather than big hydraulic fracturing, you can create a lot of surface area for the rock to react with water and other catalysts. So that's good. But then, indeed, like Richard is saying, how easy it's going to be to produce all this hydrogen that's generated around a stimulated well, how easy it is to produce all this hydrogen back to surface and ideally produce it back without having to produce all the water and catalysts back. This is going to require a lot more research.
You can't imagine it in the UK. The public would not support fracking and sticking chemicals in the ground. It would just be a non-starter. Anyways,
okay.
Sorry.
Just a couple more then before we wrap up. Let me get this question up. So, Justin Alexander says, is hydrogen expected to be looked for and then found at totally different locations / regions and different depths compared to oil and gas? The reason Justin asks that is mankind has drilled over 2 million wells in our exploration and production of oil and gas, but we don't encounter hydrogen accumulations, or at least he hasn't heard of oil and gas exploration wells hitting hydrogen. Any thoughts on that? Max, I wonder if we could maybe start with you and then we'll head to Richard.
Yeah, I think there's a variety of reasons which can explain away, if you like, why we have not found it despite drilling 2 million wells or thereabouts. Some of those reasons are absolutely very valid, given that there's a likely reaction of hydrogen with oil and gas. You're looking for a different type of source rock, amongst others. You might not have the right kind of technology and so on. But the fact that we haven't, if you like, serendipitously encountered it, other than maybe Burakabuga, although that was a water well, which happened to encounter hydrogen, it shows that it is not easy, for sure. But we might need to look indeed at quite different places, and those are underexplored, and they have potential.
Richard, any thoughts about that?
Well, drilling oil and gas wells, routinely people don't record for hydrogen. So you're never actually looking for it. So therefore, that's why you've not observed it. There is an oil and gas well in Brazil, Petrol 1 in the Sao Francisco basin, that was a conventional oil and gas target that encountered a reservoir with, I think, 40% methane and about 39% hydrogen, which was quite interesting. But obviously, if we're looking for green energy, we're probably looking to avoid drilling for hydrogen in oil and gas provinces. So I think we'll be looking in different geological areas.
Thanks, Richard. And it's important, really important to follow the mapping there, isn't it? And let that do the work for you in terms of where you need to go. That's going to be really important and a really important aspect in terms of developing that mapping technology and approach as well. Final question here. I'm wondering if we can really quickly touch on it. Tim Davis asked, what impurities and other gases do you expect with the hydrogen extracted? Mali is very pure, but other sources appear to have a lot of methane in the mix. very quickly, can we touch on that?
I would say that is indeed certainly a challenge. Don't think that any company out there yet who can say, I can predict what other gases might be associated with hydrogen. So at this moment in time, it is drill the well, do your analysis, and hope it's pure hydrogen. But if it's a lot of CO2 combined with it, that certainly is challenging from a commercial point of view, let alone from environmental concerns.
And do you move on then, or do you develop the technology to extract?
I would say it depends what it is, but we certainly can extract it and put the CO2 back in the ground. Richard just referenced Brazil. There are fields with large CO2 concentrations as well, which are being developed, but at a certain point, the concentration might be so high that it becomes uncommercial. So it really depends on the total mix. The upside, again, hey, I'm the glass half full guy here maybe today. There might be highly valuable gases in there. And what we see quite a bit is helium, for example, being associated with it. And helium is extremely valuable, and there's actually a shortage of production of that across the world. So that certainly could be a nice upside.
Thank you, Max. Okay, I suppose last thing I'd ask then, kind of looking forward now. I think this conversation has shown that there is certainly potential and things happening, but the scale at which we develop those well tests and gas flow tests and the scale at which we look for this natural hydrogen really needs to ramp up and increase. What do the panel think? What's the one key thing that we need to do now in terms of stimulating investor confidence and growing this market and making people aware of its potential? I mean, I think, Richard, you'll agree it's really good that we're seeing these reports come from the Royal Society and the British Geological Survey. It shows, and I think that was commissioned by the Department for Energy Security and Net Zero, so it's clearly on their radar, which is good. What needs to happen now in order to grow this market and stimulate that investor confidence? Richard, I suppose we'll start with you. We'll move to Arnout, and then Max, if you have any final thoughts.
Well, thank you. Well, the easy answer is for someone to drill a well that's successful and tests, at what might be commercial rates. That will drive everything. But it's not going to be easy, and there will be a lot of disappointing wells drilled before that happens.
Yeah. Arnout.
Yeah, I agree. It's basically drilling a well that proves a substantial amounts of gaseous hydrogen, so hydrogen gas in the subsurface, and then ideally flow testing it. Say almost more than a flow test. What I'd love to see, and I haven't seen any example so far, is basically a gas gradients from downhole pressure data. So normally in a natural gas, when it comes to certifying a resource, so showing potential investors or buyers, demonstrating evidence that this gas is there and that the amount of gas is, that the seller is claiming is there is really substantiated by subsurface data. Well, key evidence is downhole pressure data, where you can show that pressure points you take at different depths, that they line up along a so-called gas gradient, so a gradient where the change in pressure with change in depth reflects the density of gas, not the density of water. And I haven't seen any example of this from any well drilled basically with hydrogen gas shows. And to me, this is a starting point. If someone wants to convince me that there's substantial amounts of hydrogen gas in the subsurface, then I want to see a gas gradient.
Max.
Yeah, I would step maybe slightly further back. And what we really need to continue to see is investors with very significant risk appetite to push the envelope of our knowledge further outward. And being that of the subsurface, as well as technologies to extract hydrogen from what currently seems to be uncommercial sources. And I think this stuff being done by Breakthrough Energy and other of these kind of investment funds is great in that sense. And of course, the question is how long do they continue to have appetite? Certainly, we'll see commercial success before that. But at this moment in time, their continued investment and their equivalence is what we need.
I think it's a beautiful thing right now in such nascent markets like this. It's we can tend to get quite competitive in our industries. I think it's a lovely thing that everyone in this market is preying on the successes of each other right now. I think that's a really good thing. Is as you said, Richard, we just need that successful drill that shows that this can be developed at scale. So so that's a really good thing, I think. And you see a lot of cooperation rather than competition at the minute, and I think that's a good thing. Fascinating discussion. Thank you very much indeed to the three of you for sharing your expertise. I know we've gone a little bit over, but I think it was good to get into a few of those points. Thank you very much for all of your very stimulating questions from the floor as well. I think that's probably a good place to leave it now. So once again, thank you very much, Max, Richard, and Arnout for joining us. I think that was a fascinating discussion, and I think watch this space is the key word here, and see what happens now. And wishing all of you the best of luck in whatever ventures you're doing. Thank you very much indeed for joining us from the floor as well, and posing your questions. As I mentioned at the start, this webinar is part of a series of webinars looking across the energy mix in the UK, and as we've seen today as well, outside of the UK too. Our next webinar will be in 2 weeks. We're shifting focus significantly here, looking at data center energy and how we meet our data center energy requirements to allow for balanced AI and digital growth. I think that'd be a really good one. I've just popped now into the chat as well a link to the Foresight event taking place next February. As I said, that's an all energy clean tech show where we'll be looking at all of these sectors and how they fit together as well. If that's of interest, please do feel free to click that link and have a look. But for now, thank you very much once again. We'll leave it there, and we hope to see few of you at future webinars as well. So thanks again, and take care, everyone. Bye bye.
Thank you all. Cheers, Terry.
Thank you.
Thanks very much.
Bye.
Bye-bye.
Take care. Bye bye.